This is the lesson video for 7-1 Day 3. Take a look at the warm-up, pause the video, see if you can answer the questions with good explanations, and then come back. If you're back, you were trying to figure out without doing antiderivatives, taking this function that they gave us, dy dx equals the opposite of x. Don't want you thinking antiderivatives. I purposely gave you a simple derivative so that we can think ideas. If we tried to give you one that you'd actually need to use for this, that using an antiderivative wouldn't work for, it'd be a little too complicated. So they say dy dx equals the opposite of x. They are telling me slopes at different x's. These are the slopes that my y function's got to display, the opposite of its x values. And they're telling me that my graph has to go when the input is -1, the output has to be 1, and all of these graphs had at least that characteristic. So that alone won't solve the problem. However, when it tells us the slopes at any point, that does tell us which one of these it has to be. So it can't be A, because when x values are negative, that would mean that the opposite of my x values would be the sign of my slopes. That would tell me that I have to have positive slopes when x is negative. And I don't have positive slopes in this first part of my graph. I have negative. In B, however, I do have positive slopes. For all my negative values of x, all the slopes that my function's displaying are positive. B also the reason it can't be C. For negative values of x, my slopes would have to be the opposite of x, or positive, and all my dy dx, or slopes on this graph, would be negative. So in good words, you'd want to be specific and explain how you know why one of those cannot be the y function whose derivative is opposite of x. So you've done a couple things in order to solve differential equations. And many of you are saying, if I know antiderivatives, why can't I always use that? Well, two things. We aren't always going to know the antiderivative for something. And second of all, even though maybe some other calculus person would know more antiderivatives than we would, there are still functions where antiderivatives really aren't easily gotten. And therefore, there are methods to give us faster and more quickly an idea of what that function should look like or should have as its characteristics. So methods we've had so far for examining or solving these differential equations, the first one is to use slope fields to get an idea about a solution. So if this is my slope function, my derivative or differential equation, and I'm interested in what it can tell me by making a slope field, I would at every x make sure that I put that in. So when x is 1, my slope should be 2 all the way up at any x value. So if I looked really close at the graph of this, the slope should be around 2 at 1. The slopes at 2 should be at 4, at 3 should be at 6. So this gets steeper as x gets bigger. It also is negative slopes coming towards 0 as we move from very tiny numbers, -infinity, up towards 0. So here's some things I know, and some reasons I would use slope fields is I might not know an antiderivative, but I can tell graph features. For instance, from this equation and the slope field alone, I do know that my function has to have a minimum at x equals 0. And this is going back to some of our ideas about extrema. And when you found out where graphs had extrema, you found out two things. You had to show that the derivative at that particular location, so my derivative when x is 0, is 2 times 0, or 0. That's one thing. In order to show I have a minimum, I have to show its derivative is 0. In other words, that it's a stationary point on my graph. But then I have to rule out that my stationary point might actually just be a point of inflection. So I need to prove that my derivative on either side changes from positive to negative or negative to positive. So my dy dx information is that when x is 0, I have 0 slope. However, when x's are negative and I plug them into 2x, I get negative slopes, so my y function is decreasing before 0. And when I put positive x's in, I get a positive dy dx value. That means that my graph of y is increasing afterwards. So a little first derivative test to confirm that I know that information. So slope fields aren't always going to give us the equation, but they're going to tell us some characteristics or things that we should be able to tell about that y equals equation that we have the derivative of. Secondly, and this is the most popular one, because people, I think, just feel the most comfortable, if we know antiderivatives, then we could solve a differential equation or an initial value problem explicitly using antiderivatives. So by initial value problem, remember we're referring to most differential equations because usually we get a little more information. All right, they're telling us the derivative and they give it to us. And looking at both of these pieces of the derivative, both terms, I think I know an antiderivative of that. And I think I know an antiderivative for that. So okay, I could probably solve this by antiderivatives. And then it's got to have a specific constant because they gave me information about what point the graph also has to hit. They're telling me the graph has to be at 0, 3, so that would limit on my slope field which form of the function. That's going to change that plus constant that we would put as a general solution. So first I'm going to separate my differentials because, again, if you're going to use this method, you need to make sure that your calculus is solid and your notation is good. So on this side, if I want to multiply by dt on both sides to get off that left-hand side, this side needs to become a single quantity that I can do that with. So that's why the parentheses are here. Then I'd like to multiply that by dt to bring my differential over. And then I left a little room so that I don't have to rewrite, and I can go take derivative of each side so that I can work out my antiderivative. So the integral of dy is y. And then the integral of each part of this by integral rules, and this is an indefinite integral instead of a definite. I've got no lower upper bounds. I do know the antiderivative for this is inverse tangent. This would be of t. And then I do know the derivative for, the antiderivative for that is 2 to the t. And then in general solution form, I'd put a plus c. This is my general solution. Anything that's in this form has the derivative we seek. But anything that's in this form does not necessarily go through 0, 3. So to get a specific solution, I need to go back and actually input those two values and find out what that constant needs to be. So I need a y value of 3 when my t value is 0. Please be careful when putting zeros in. A lot of people forget to actually go calculate that c, and they just assume that all the terms that the 0 went into become 0, and that isn't true. Inverse tangent of 0 is 0. 2 to the 0 is 1. So the constant we would need to be a specific solution here is 2. And then you have to go back and actually answer the question. You can't just leave this work here and say, well, my constant's 2. So in answering the question, solve the initial value problem. My specific solution needs to be inverse tangent of t plus 2 to the t plus 2 in order to have the derivative that they seek and include the ordered pair 0, 3. So that's my specific solution that they seek. So antiderivatives are a great way to solve a differential equation if I know the antiderivative of the integral that they gave me, of the derivative that they gave me. And finally, here's where you may need to spend some time and come back and watch parts of this video again. We can also use fundamental theorem. Fundamental theorem guarantees us that if that's a derivative, that there is an inverse function, meaning there is an antiderivative, that there is a function whose derivative is that, even if we can't find it. So fundamental theorem is going to let us work backwards a little bit. Here's what we knew from fundamental theorem before. We were guaranteed if we took the derivative in terms of x of a function from a constant, and sometimes that constant was specially picked, to a single variable, usually in terms of x, of some function that wasn't even in terms of x before, the derivative of the integral was going to come up this. So we're going to use that kind of in reverse. we're going to say, well, what if they tell us the derivative and we have to get back to what that antiderivative or what that function came from? So the kind of the opposite direction of where we were in the last chapter, where you'd get the derivative of an integral and you had to simplify or find it. They're saying, can you work backwards? So they're asking us, if this is a derivative, if this is a dy dx, and it's equal to e to the negative x squared, they're asking us to back up and see if we can come up with, well, what was all of this that let us come up with that as its derivative? So as we go to back up, the derivative side here is saying that e to the negative x squared was the derivative of some integral from a constant to a variable. So I'm looking for my constant, I'm looking for my variable, and it must have been x to put it in terms of x in our final, but that it was originally a function that was in another variable, e to the negative t squared dt, and then maybe there was a constant here afterwards. We're going to have to figure out two things, what that base constant might have been, and then what that plus c constant might have been at the end, so that by the time we're done, we can come up with the y equals function that this came from. So since we're taking and looking at whose derivative this is, we're going to end up saying, okay, if this was the derivative, then the y function was. And the y function was, again, kind of saying both sides have a derivative in that sense. The y function was this integral from something to x of e to the negative t squared dt, and then plus constant. So that'd be kind of our general solution, a plus c kind of thing. Then I'm going to go look and see what they told me. They told me when 7 goes in as my variable, 3 has to come out for the y. So 3 has to come in when I do something from something to x of e to the negative t squared dt, and I add a constant. So, okay, so let's see. I do know what would happen if I input 7 up on top as long as my base was 7. If my base constant was 7, then if I input 7 as x, my entire integral part would be 0, and therefore that constant that I'm missing is just 3. In other words, I could get this whole thing to 0 out if I put 7 in. So my equation that I'm looking for is to make my lower bound 7 and my extra amount after the integral is evaluated 3, so that this function has a derivative of e to the negative x squared. And again, using fundamental theorem to reverse that. So 2 problems to see if you can come up with following that same lead and getting their integrals, in other words, getting their initial value worked out so that we can see what the function was. Pause the video, work these 2 out, go back to the previous example. There's no sense in just copying these down if you're not actually trying to think them through. Okay, if you're back, that means you spent some time on this. Without spending time on this, this part won't get any better. And I will send you back to the video if you say, can you just walk me through it again? Okay, because if you're not asking me some questions about the specifics, that means you need to go back and hear it again from the video. So taking a look at these 2. So again, I want to go back to that fundamental theorem idea. My derivative, if it's this, that came from the derivative of some integral. And so that's what you see next, the derivative of some integral. So the derivative of some integral here. And so if we had to do it in general terms, there'd be a plus c after this. But we know when x is 1, we'd like this to come out 5, so there's my specific solution. Same with the other side. Okay, pause video, go through them again, go back to the example, go back and look at some things about fundamental theorem to try to wrap your head around this a little bit, because this one's a little tricky. So again, we want to use that when we really don't know an antiderivative. Slope fields aren't necessarily going to tell us a whole lot or aren't really feasible for some of the values that we have that get a little crazy. So finally, here's your 7-1 day 3 assignment.